So as we've heard from many talks in our workshop this week, there are many challenges that we still need to address with new metrologies, in particular for dimensions less than 100 nanometers, and in particular for functional imaging. Chris mentioned that one of the big advantages of coherent imaging and X-rays is the ability to penetrate thick samples. But when we have coherence, and we can have coherence in space and time, we can also have stroboscopic probing. And compared to the visible techniques or the static techniques we use now, this can really allow us to access new materials measurements. And so, of course, we're all in this in this quest together. We very much need microscopes and methods that can see better and see things as they function. And of course, we all have our favorite way of probing materials. And the nice thing, for those of us as we're either new to the area or we're experts in this area, that no one technique is, will cover all we want to know about materials. And so it's wonderful that we have this whole array of visible, electron, short wavelength, and also other probes like nanoindentation, focused ion beams, all of this. And every one of these probes have their advantages and disadvantages. And I won't go into details. I think many people are aware of this. In our group, we primarily use short wavelength light, and we love it because it can tell us what the instantaneous magnetic state of a material is, for example. It gives us elemental and chemical specificity, and it can be non-destructive, so we can take a piece of material, pop it in a microscope without needing to fib or cut a small piece of the sample. And that turns out it's very nice for semiconductor or magnetic multilayer samples, for example. And then we also get the benefit, because we have short pulses of laser light, to stroboscopically probe the transport, the elastic, and the spin properties in nanostructures. So today I'd like to talk about this functional probing of heat transport and also the elastic properties of very thin films. And it turns out at dimensions below 100 nanometers, people have traditionally been using visible lasers or techniques such as nanoindentation to probe these kinds of materials. The problem with nanoindentation is essentially, you're pressing on a material. If you're pressing on a very thin film, the elastic properties you measure are actually that of the substrate. And similarly, if one wants to look at how heat flows in nanoscale devices, if you use a visible laser, then you need a model to actually extract what the scatter data is telling you. And those models, what we're finding, and this is in collaboration with experts in the area, they're actually wrong. It's not that anybody, people are super smart, it's just that if you can't see the behavior, you're not going to design a model to actually, you're not going to be able to iterate the model. And so then you get stuck. I won't have time to talk about spin transport, but it's another area that is really suited for these ultra-fast X-ray probes, because normally these probing is done with visible light, but if you shine a visible laser on a magnetic alloy or multilayer, you will measure the average magnetic state. But there's a lot that can go on in different elements of the alloy that can make those measurements not accurate. And then there's another area that I won't talk about, but trying to understand quantum materials. We're finally, and we, I mean our community, is finally understanding how to probe very interesting many-body interactions in quantum materials, and trying to understand what ones determine the ground state. And it's taken our community quite a long time to be able to get there. Okay, so in particular, I'll cover two areas. Reflection mode coherent diffraction imaging. We heard a beautiful talk by Ian this morning. And in the EUV, it has particular advantages because at glancing incidence, one can get reasonable reflectivities at relatively longer wavelengths on order of 10 nanometers or longer. And then I'll talk about the nanoscale thermal transport. In ongoing work with John and other colleagues, what we'd love to do is take the beautiful 3D vector typecode tomography that he and Sten developed the method for, combine it with our ability to see super fast dynamics in magnetic materials that happen when they're excited by light, but that EUV was necessary to be able to see what was happening. We'd love to combine those two capabilities together to be able to dynamically image spin texture. We're a long way from being able to have the methods or the ability to handle the data that would be associated with this, but it would be super, super interesting to study magnetic systems. We still really don't have any general models of magnetism. So as I showed earlier, we use tabletop EUV sources, and we can tailor the light, the laser light, change its color, and in that way change the output EUV spectrum, and also its properties, both its spectral properties as well as its polarization and orbital angular momentum. And what I quote here are just the current types of photons per second that is possible to generate in these in about a 1% bandwidth in these regions of the spectrum using a 10-watt laser. If you can always build a bigger laser, but we have facilities for that, and we're talking about systems. We like to use systems that a graduate student can learn to operate, that fits on a fraction of an optical table, and that are quite good for university-based research. Okay, so we've heard a lot about coherent diffraction imaging in the workshop this week, and heard the beautiful work of at the facilities at APS, at Cosmic, and I'll talk about these two reflection mode capabilities, one in a full field imaging mode and the other in a dynamic scatterometry that lets us probe transport. So of course EUV won't have the beautiful spatial resolution that shorter wavelength X-rays has, but it's very good in that if you look at the reflectivity shown here as a function of glancing incidence angle here, for different materials, whether it's silicon nitride or gold or silicon dioxide, lithium, carbon, arsenic and such, there is very nice intensity contrast, and there's even better phase contrast. So what that means is that we can use it to our advantage on samples where we don't have a lot of spatial heterogeneity. And of course these would be semiconductor and things like that, where they can make very good devices, and it would be nice to be able to probe them non-destructively. So to do that, this is a multi-year effort by mainly by 3 graduate students, Chrissy Porter, Michael Tang-Savala, and Yuka Asashi, where we learned how to extract reasonable quality reflection mode images. So the first microscope we built was relatively primitive. It just worked at one angle. We had a high harmonic source, a little ellipsoid that focused onto a sample, and then collected the diffraction pattern. But of course, at that very high angle of incidence, you're going to have a distorted diffraction pattern. So the first thing we had to figure out is, so how are we going to map that tilted diffraction pattern onto curvature corrected diffraction pattern? So we learned how to do that. And then in this first microscope, we just have a homemade sample, so it's just a little a sample we made ourselves, but we were able to at least show that the tilted plane correction worked, that we could extract a reasonable quality image, and then compare, for example, the EUV phase imaging with SEM imaging. And similarly, you can see what people talked about earlier, of course, the carbon contamination that is accompanied by any imaging modality. And then more recently, I don't know why this film, we embarked on the royal we, Michael, Yuka, Nick, and Chrissy, developed what is our most complex microscope to date. So it's an imaging reflectometer where we can implement near glancing incidence tychography as a function of angle. And so, the programming to get this, all working was actually quite intense. So this is a little, just a cartoon of the reflectometer. And then we were fortunate that EMEC provided a nice sample where it had, I have a better, okay, I'll get to that. I have a better picture later, where it had complex structures that were not fully periodic, and then also dopant, different interfaces, and this was a much better sample than the little thing we were able to make in our local nanofab. But so this is tychography, and then you extract the images as a function of angle, and then we have to use models to actually build up the sample. So we do the tychographic data, correct for curvature, then do the phase retrieval, then measure the reflectance as a function of angle, and then correlate that with a genetic algorithm model so we can actually fit, and then be able to fit, the interfacial thickness and such, and see what agrees with our complete data set. We even when, we unfortunately Boulder doesn't have the beautiful, data groups that APS and the ALS has. So we used Google Cloud, but we still couldn't actually analyze all the data. So we were still limited by what we could load up on our little NVIDIA machine. But the nice thing about the EMEC sample is that they had we had a design file, and that, it had like big pads, so we could locate this with visible scatterometry, and the multi-scale structure means that we had a way of navigating our way around the sample, because we were learning how to do a material sample. So it had dopant period. So for example, some areas in the sample had real gratings, and the other areas had just dopant gratings. And so we were sort of interested, could we see a pure dopant grating, which or not? So it turned out that the etches are different when the sample is doped or not. So it ended up having there was a tiny shallow grating where there was some dopant. So we could cheat that way and actually see the dopant gratings anyway. So took us a long time, and we had a lot of help from John and Laura and other people in learning how to extract the image. So this would be just a typical 2D scan, and these are 2D scans at different angles, which are shown over here. If I can get oops. So these are 2D scans at different areas, and this was before we implemented, for example, total variation regularization, and you can see the improvements here. And I think some of these lines are real grating lines, and then the other lines are dopant lines. And what we found interesting is, you can get a low quality image of a very large field of view, and a high quality image in areas you've got good tychographic overlap. So this center orange region here has 90% of the photons, then 99% of the photons is in this region, which is still pretty good, then 99.8% of the photons are here. So it's sort of nice that we can actually get, relatively large areas. So this is like a 50 micron region. And then over time, we learned then to extract the spatially resolved map as well as the dopant profile, and that dopant profile in different regions of the sample, because some parts of the sample had these nanostructures, other parts had none, and so we could look within the nanostructure, under the nanostructure and adjacent to the nanostructure, and have a reasonable profile. This is not a direct measurement, it's an agreement with a model that modeled the reflectivity and phase image. And then, of course, we had to correlate with atomic force microscopy and TEM to validate what we were extracting. And so you can see here is, for example, this is the phase image from the reflectometer, and this is an atomic force microscope image. And of course, AFM has intrinsically higher spatial resolution, but it can't tell you what elements are under, the dopant profile. So we made maps, and tables saying, well, what could we measure with this approach compared to what one can do with electron AFM and SIMS imaging. Okay, and then we were happy that our colleagues at EMEC are adapting this. I think I showed this in the talk on Tuesday. Just like we do in our lab, except that we're looking at much more fundamental questions. They would like to, for example, use photovoltage or simple photoelectron spectroscopy, that when you integrate different 2D materials, what is happening at the buried interface. And it turns out Rich Hyde at IBM had developed that approach maybe 15 years ago, being able to probe buried layer bending, but also just looking at nanostructured systems. I showed this before just to give an idea of the spatial scale, and the system at IMEC looks a lot neater than the systems in our lab. And so, this is the laser and 2 EUV sources, and then different, small beam lines that can do the angular resolved photo emission or the coherent diffractive imaging or pump probe to understand photoresist, for example, or other types of materials, and then the interference lithography and EUV mask coherent diffraction imaging. And they've already, EMEC has already shown some very nice 20 nanometer pitch, full pitch resist exposures using harmonic sources. Without even focusing, you can get a nice grating pattern exposed in a minute, and focusing that can, with the focus beam, you can do a lot faster. Okay, so what about periodic samples? We had imaged a zone plate, which is a near periodic sample, back in 2017. But when we tried to do this imaging, we noticed that the quality of the images were very sensitive to how we set up the experiment, and we didn't quite understand what was determining when our data set would give us a good image and when it would not. And so we started to think, well, how could we increase the diversity in the scatter patterns? And so we thought about doing something like we heard from Monica. Could we use an OEM beam with phase in the beam? Would that help? So it turns out it's a very easy thing to do with high harmonic generation. And of course, we heard from Monica all the reasons why OEM beams, and earlier why being able to control the polarization state is very nice. But the nice thing about high harmonic generation is that if you do a simple implementation, the OEM is conserved but multiplied by the harmonic order. So that means, you're going to have a higher OEM with higher divergence if you use an OEM beam compared to a regular beam. So, and then of course you can play tricks. You can combine different beams, you can combine different angles, and then you just use selection rules to see what sort of beam you end up with. And we got pretty good at this. These are nice light science experiments for us, in that we can make OEM beams where the different polarizations, the different circular polarizations have different divergence and OEM value. So that seemed it might be useful. And then we could make beams where the OEM or the shape changed during the beam. However, it turned out in the end, what mattered is not the OEM. It took us a while to figure this out, but rather whether we were imaging a periodic sample, like shown here, and whether the divergence of the zeroth order overlapped with the next orders. And so in so here we have the situation where there's no overlap between the different orders, and of course it's very periodic because the sample is periodic. And here with OAM, the nice thing about OAM is all we had to do to change the divergence was to plop a phase plate in the driving laser beam. So we didn't have to change any optics, or we didn't have to change an aperture or anything. So we dropped a phase plate, and that automatically then gave us a beam where most of the intensity was in the vortex part. And of course, then that overlaps really well and gives a lot of interferences between the adjacent orders. So it was just a convenient way. I wish the phase mattered, but it didn't anyway. But it did matter for the reconstructions because, you know, when we, and this is Nathan Brooks and Bin Wang, so when they would try the phase retrieval on the case where there was no overlap between adjacent orders, we wouldn't recover the little 20 nanometer carbon foil that was highly periodic, but you know, you just couldn't retrieve. But then as we used the diffraction data with overlapping orders, it was able to retrieve the images very quickly. And along the way, of course, and we've been discussing this earlier with Ian's talk and many other talks, is that you get out the amplitude and phase of your illumination also. So this gave a nice image of the OEM beam, the high harmonic OEM beam that we were using with the phase, also with the phase, which is sort of nice. So, so this enhanced sort of fidelity imaging is just based on essentially the NA. You can reproduce it by putting an aperture in the beam and blocking the center, and we verified you could do that. So we actually knew, you know, if the phase mattered or not. And so this is just sort of sanity checks. You know, are we, as we carefully tune the NA, does it matter if we have phase diversity in the illumination beam or not? And this is just another check of that we don't see. These are simulations, and we just don't see any difference between a donut beam and a vortex beam, I guess is the way I would phrase it. So the donut beam you could make from a Gaussian beam by obscuring the center. But, and I showed this on Monday, we were sort of excited to see that we could see a defect where there was a scratch on one of the 20 nanometer thin carbon lines, and we imaged it multiple times, and then when we stuck the same sample into the SEM, we could see line shrinkage immediately due to the SEM beam, and not, and of course that's sort of, you know, it's nice to see. Okay, so then in the last part of my talk, I'll talk about the functional imaging of heat flow, and as I explained previously, the issue here is people have been using thermomodulation for a long time, where you can't look at very short time scales, because when you heat a material and then reflect visible light off that material, any charges that you make will change the refractive index, so you can't tell the charge signal from the heat signal. EUV is completely blind to that because it doesn't care whether the electrons are in the conduction band or the valence band. So with EUV, all you see is the height difference between the top of the nanostructure and the bottom. So you really are just measuring the shape change due to heat flow. So it's harder to fool oneself. And we can, and because of the previous limitations with using visible light, essentially people have been modeling either nanoscale hotspots or heat flow in nanostructured materials as ballistic. So assuming that the phonons scatter, and the scattering is determined by the geometry. But it turns out we know that phonons do interact. So it's not, phonons are not photons. So, you know, in a photon picture, you will scatter if you've got a reflecting object or a diffracting object. But phonons interact with each other. There are anharmonicities. So it turns out what we're finding from the experiments is that phonon nanoscale phonon flow acts a little bit more like water, a little bit more like hydrodynamics, because since they interact with each other, they can flow through necks, for example, small channels, and there can be, because of the interactions between phonons, this means that a larger part of the phonon spectrum can participate in heat flow. And since you couldn't see this with visible light, the fundamental models were not complete. So this is work done by Josh Knobloch, Emma Nelson, and Brendan McBennett, the experimental team, and Albert Biardo is a postdoctoral fellow from Barcelona. He came from one of the theory groups that we're working with on this topic. Okay, so the setup is shown here. We have metallic transducers that we put on either a substrate or a thin film, and then we heat those transducers with a laser beam. And for example, if this was metallic transducers on silicon, the 800 nanometer is only absorbed by the metal transducers, but not by the silicon. Then they expand and shrink, and in this geometry, this would simulate a transistor switching, for example, and then in the nanoscale materials, it would simulate, for example, a nanostructured thermoelectric, where you're trying to impede heat flow but maintain electrical conductivity. So this is just the same setup, but it shows the data. The data is beautiful. This is on a nanosecond, so it goes up to 7 nanoseconds, and what one can see is one can either look at the slow decay, which is the heat flow, or the modulations on the surface, which are acoustic waves that allow one to extract the full elastic tensor. Okay, so we've done with collaborators at Penn State and Barcelona and aerospace engineering. We've looked at a lot of different systems, and in each case, very interesting reviews. Because when you're seeing something new, it takes a while for the community to accept that. But over time, we've been able to do that. And so I mentioned before this idea of that the idea was that phonons travel ballistically, of course, and that, but as and of course the issue here is that there are methods such as doing a full Boltzmann transport equation that could model heat flow on a fundamental scale, but it's too computationally intense to apply it to a real experimental geometry. And that's part of the challenge, why it's been difficult to come up with full theories. It's a very active area, and the first experiment that sort of made us sort of realize that we really needed to understand this as a fundamental level was when we looked at heat flow from closely packed nanolines and spaced apart nanolines, and we found that although the heat density in this case is much higher per unit area, the heat flow was still faster away from the closely packed nanolines. And this took quite a while. We made a phenomenological model as to what must be happening, but since there was no fundamental theory, it had a hard time being accepted. But very recently, we now have both an atomistic theory and a hydrodynamic theory that both agree, where we actually understand better what is happening. So what is happening is that when one takes two, let's say, hot nano lines and places them closer together than the mean free path of the phonons in the substrate, then there can be increased scattering in plane, and that is a good temperature gradient that then drives increased transport into the substrate. And both the molecular dynamics models and the hydrodynamics models both sort of it gives the same types of heat profile. So for example, if one was to apply Fourier law, you would say that the regions adjacent to that hot nanoline, that should be as hot as the region of the substrate underneath, but it's not. And it's all got to do with, what photon scattering can happen in these materials. So this is sort of an effort to show a cartoon that these increased cross-plane scattering then drives increased in-plane scattering drives higher cross-plane thermoconduction. And just showing, how different this is. This simulation is assuming periodicity, but this would be Fourier law, and this is the molecular dynamics calculations by Mahmoud Hussein's group in aerospace engineering, just showing, how different it is, how different nanoscale heat flow is, and again confirming that you get these sort of bubble-like heat profiles, either with the hydrodynamic transport equation is valid for scale lengths greater than 100 nanometers, and then the molecular dynamics simulations are valid for scale lengths under 100 nanometers, and this just shows, we experimentally probed that whole length scales, but this shows that to the ability that we're able to say anything intelligent now, that's the same picture sort of holds, and the same designs can be used to try to engineer heat flow. So this is interesting. Right now the clock rates in transistors are limited by just the thermal management, and now we have ways of at least modeling in 1D, and also the same models also work in 2D. This is a very complex slide, and it's only there to show that if there is a black and blue line here in this area, so it's heat flow in 1D and 2D hotspots, and the black and blue lines, which are the theory and the experiment, do agree very well, as do the heat flow behavior. And so I think, how am I doing time-wise, Oleg? Okay. So then in this last topic then, we moved away then, with the help of colleagues at Penn State, moved away from hotspots, whether 1D or 2D, and now into heat flow in more complex geometries, for example, nanostructured metal lattices. So these would be the silicon version of the metal lattice, the magnetic metal lattices that John talked about on Monday. And again, these were modeled by assuming ballistic transport. So the geometry then would matter, because that would determine the scattering. And so that meant that since the Boltzmann equation was too complex to apply to one of these structures, what people would do is do a different calculation for every different structure. So it was very hard to make any generalizations. And so here, again, and we haven't solved this problem, we just have seen general behaviors. So that's what I'll just try to describe now. And this was another interesting material to look at, because we had to use electron imaging and X-ray scatterometry to get at these the heat flow properties, because we had to know the porosity. We had to know the actual structure to be able to understand our data. And of course, for that, then we needed a nice tomography, and that allowed us to, so the head of STEM tomography allowed us to do that. And then our colleagues at Penn State laid down the nanogratings, which we heated, and then we compared, as before, now we'll compare hydrodynamic transport and atomic calculations, and one sees sort of a similar behavior as described earlier, that there are behaviors that do not agree, that look more like a hydrodynamic flow of heat rather than ballistic flow of heat. And so and we also quantified both the elastic and the thermal. So this is the elastic properties. Interestingly, for the thermal transport, so we came up with again a nice sort of hydrodynamic interpretation, where for bulk silicon you'd expect a thermoconductivity, a very high thermoconductivity on order of 100 watts per meter per Kelvin. This is nanostructured, so of course it'll preserve some electrical conductivity, but one would expect that the thermoconductivity would be far lower. So that's not necessarily a surprise at all. The surprise was that once we took the same hydrodynamic understanding and applied them to these nanostructured materials, that Albert and Josh found a sort of a general way of plotting this heat flow, but that applied for metal lattices, for lines, for nanostructured materials, porous networks, nanomeshes. And so this is phenomenological for now, but what they found that, if you plotted the conductivity as a function of porosity, it looks like there's nothing general happening or nothing predictive happening. But if instead one plots the viscosity as a function of porosity, and the viscosity is a term that quantifies the hydrodynamic contribution to heat flow, so the deviation from ballistic, that you find that all of these much different types of nanostructures all lie on this universal curve. This is a sort of a phenomenological finding, but now, of course, what we want to do is challenge our theory collaborators to see if we can find out why do nanomaterials behave this way. So we have but even with this, what this has done is validated this idea of viscosity also for nanostructured materials. So now we can actually predict heat flow in general semiconductor nanosystems that can be used by engineers for device design, although we can't explain it from a fundamental perspective yet. And so with that, I'd like to again acknowledge the team who did the work, and thank you for the opportunity to be here.